Greetings and welcome to the Chemistry 222 lecture for Chapter 8. The title of the lecture is kind of long, Bonding and Molecular Structure, Orbital Hybridization and Molecular Orbitals, but what it comes down to essentially is comparing the two models used to describe the behavior we looked at in Chapter 7. So all of the Lewis structures, Vesper geometry, stuff like that works pretty well, amazingly well actually. But why does it work? And in this section we're going to look at the two models which are used to try and explain like why tetrahedral comes around when you have four clouds around a molecule, stuff like that. The two types of theories used are called orbital hybridization and molecular orbitals, and we'll look at both of those in this particular chapter. And again, the goal of this whole section is just to understand like why is carbon with four hydrogens around it tetrahedral? Why is carbon linear in carbon dioxide with two double bonded oxygen? And when it comes right down to it, we need to explain how atomic orbitals, these are the 1s, 2s, 2p kind of things. How do you take those orbitals and make molecules? And this is actually a more important question than you might at first think. The circle part right here is an s orbital, and there's no angles associated with it at all. And the other three pictures right here are all different p orbitals. And if you remember, p orbitals are kind of like a figure 8, and they're at 90 degrees from each other. So one is x, one is y-axis, one is z-axis. But how the heck do you take these types of orbitals, which at best have 90-degree orientations with them, and s's don't have any angles at all, how the heck do you turn it into tetrahedral CH4, which is what that picture is on the right? And remember, a tetrahedron has 109-degree angles. There's no 109-degree angles in the atomic orbitals. So these theories we're going to look at in this section will try to describe how you go from the atomic orbitals into essentially the orbitals in molecules. And again, there's two theories to explain this. The first one, and arguably the best one, is called molecular orbital theory. It was developed by a scientist named Mulliken, all right, and it's really cool. In a molecular orbital theory, you can actually take the atomic orbitals and do some cool things with them. In molecular orbital theory, which is sometimes abbreviated MO theory, the valence electrons around atoms are delocalized. And what that means is those electrons, they don't just exist on the individual atoms. They make like a energy shield, if you will, around the molecule. The picture on the right is a BH3, and the little green kind of, I call it shields around the ship, but I like a lot of Star Trek, okay? But anyway, those shields are made up of the valence electrons. The valence electrons literally are delocalized over the whole molecule, so it is kind of analogous to shields on the starship. And if you're not a Star Trek fan, first of all, I forgive you. It's okay. But second of all, I'm just joking about that. You don't have to like Star Trek to do well in this class. But shields were put around a spacecraft to protect it from things like meteors and, of course, other spaceships firing at them, stuff like that. So it's a kind of a cool analogy here for what's going on in molecular orbital theory. Those valence electrons are placed in a type of an orbital like they were in atomic orbitals. But in this case, they're placed into a molecular orbital, all right? And the molecular orbitals are essentially delocalized, i.e. spread around like peanut butter on toast over the whole molecule. Now, MO theory is really cool, but MO theory is also pretty complicated, as we're going to see. So we're going to look at some examples. Arguably, one day in the future, when computers become more and more compact and you have more of a phone kind of computer next to you, MO theory will dominate. But in the meantime, we do need to think about the other theory as well. The other theory is called hybridization theory or valence bond theory. They're the same kind of thing. Sometimes I will probably abbreviate this VB theory for charity. Anyway, Linus Pauling, who we talked about in the last chapter, who discussed electronegativity, was the proponent of the valence bond theory. And valence bond theory is pretty cool. Valence bond theory is something that you can literally do on the back of an envelope. You don't need a sophisticated computer or anything everything to figure out the results of valence bond theory. In valence bond theory, those valence electrons, which were spread over the whole molecule in MO theory, those valence electrons are localized between two atoms, or lone pairs for that matter. So instead of being spread over the whole molecule, like peanut butter on toast, the peanut butter is literally just spread between the two atoms, the atoms that are sharing it. If you have a lone pair, then those electrons just sit on that one atom. So it's a little bit different kind of model. In a valence bond theory model, you have two half-filled atomic orbitals, and they combine, they overlap to make bonds. So we're going to come back to the idea of what exactly sigma bonds is, and later on pi bonds, stuff like that. Pretty cool. So in this theory then, electrons are stabilized by two nuclei. The electron might have started on carbon, but then it's stabilized between a carbon and a hydrogen, or a carbon and another carbon, or something like that. This picture is something we looked at briefly in the last chapter, but we'll look at it here in more detail. This shows the ideal description of what a sigma bond is. And remember, sigma bonds are when atomic orbitals combine. They smash into each other, they go head to head, and the interaction between them is what makes the sigma bond. So this is the interaction between two s orbitals. If you look over on the far right here, each of these little spheres is an s orbital, all right? So imagine you have two, say, hydrogen atoms, and they want, if you will, to form a bond. Well, as the atoms get closer and closer, so you can see here they're closer, and here they're even closer yet, then the electrons begin to form that sigma bond, and there will be some ideal bond length and some ideal bond energy, which represents the most stable form of the H2 molecule coming together. However, one thing we didn't talk about in the last section is that if you go even closer, all right, so this little picture right here shows that as you go even closer, then you begin to have the electrons repel the other electrons more, and the nuclei repel the other nuclei more. So you begin to get to the place where you don't have any energy savings. And remember, in physical science, it's all about the energy. We probably want the ideal energy, which would be right there, and that's going to correspond to an ideal bond length, which is right there. As you get too close, you lose that, all right? It becomes unstable. It's like if you stand really close to your friend, like really, really close, or you're in their personal space. It kind of freaks people out, all right? That's kind of the equivalent here with two atomic orbitals. They can get too close to each other and kind of freak each other out.
The energy of two atoms varies with distance, according to the interplay of the attractive and repulsive forces between them.
So again, this video just shows again how there's a place, an ideal distance where you have the most energy savings, if you will. You really store a lot of energy. Too close, you don't have it. And too far away, the orbitals can't interact with each other. In the last video and picture, we showed two s orbitals coming together, which is the top one right there. And again, when they come together, there's going to be some ideal distance between the two nuclei centers. That's the best savings. And as a Lewis structure, we would draw just H-H, where again, the line is the sigma bond. So all of these are sigma bonds, single bonds, all right? And they come together from the overlap of two orbitals. And what we're looking at there in the top one then is two s orbitals coming together. But you don't have to have two s orbitals come together. You can have one s and one p orbital coming together. You can also have two p orbitals coming together. As long as you have that overlap of the orbitals, you're going to do it. So hydrogen monofluoride, HF, the second example, comes from an f orbital, and we're using a p orbital here because if you remember, fluorine is a 1s2, 2s2, 2p5. Two p's can hold up to 6. That means one of the two p orbitals has a single electron. And if you're going to make a sigma bond, you need a single electron on the first atom interacting with a single electron on a second atom. So for HF, that's going to come from a 2p on the fluorine and a 1s on the hydrogen. And when that comes together, you make HF. So again, that's the Lewis structure. Fluorine shows the other electrons, the lone pair electrons. That would be the 2s2 and 2p4 of the 2p5. Those are the lone pair electrons. They're not interacting with the bonding. It's only that one singly occupied 2p orbital which interacts with the s orbital on hydrogen. And then the last example is just something like F2. Now again, fluorine, if you did the Lewis structure for F2, you'd have 7 valence electrons on each one of them, 14 divided by 2, 7 pairs, distribute them around. That's the structure you're going to get. In F2, you would have two 2p orbitals coming together, each of them having 1 electron, and they smash together, and this kind of bigger blue part right here shows the smashing sigma, if you will. Anyway, that would be that. And up here, by the way, I didn't mention it, but this would be the sigma of the 1s interaction, and then I would argue that this right here is the sigma between the 1s and the 2p interaction. But again, sigmas come from orbitals smashing together, sticking in it. Those are all ways to make sigma bonds. So valence bond theory, or hybridization orbital theory, which is the same thing, is a really interesting phenomenon, and I think it's best just to show an example of how this works out. So let's talk about boron trifluoride, BF3. Boron is one of the elements that can make a molecule without an octet. So that means boron here only has 3 fluorines around it. It doesn't need the 4th one. Boron, beryllium, gallium, aluminum are the ones that can be under. But anyway, boron's atomic electron configuration is a 1s2, 2s2, 2p1. Remember, boron has 5 electrons total. The electrons go in 1s first, 2s, etc., etc. So how do you go from spherical 1s and spherical 2s? And these 3 2p's, they're basically at figure 8s to each other, but they look something like this. It's really hard to draw the Z. It's like coming out of the screen at you and going into the screen. I'm not an artist, obviously. Anyway, how do you go from these 90-degree P angles and no angles with the S's? How the heck do you get that into a planar triangle or trigonal planar angle at 120 degrees? And that's the question here that valence bond has to answer. So again, this is really important. How the heck do you go from the atomic orbitals into the molecular orbitals? How do you go from things which are at best 90 degrees apart into 120? Pauling said that in valence bond, what happens is the central atom is hybridized. And hybridized just means that you're taking some of the atomic orbitals and you're mixing them together. And the new orbitals that come out are called hybrid orbitals. And it's an energetic mix, if you will, of the atomic orbitals. So these hybrid orbitals are really interesting, all right? You literally take the atomic orbitals, you mix them together, and out pops these new hybrid orbitals. And because they're all essentially at the same energy, they're going to try and be as far apart from each other as possible, and that's how we get the correct geometry. So let me show you an example of this. Boron has a 1s2, 2s2, 2p1 electron configuration. I'm not going to show the 1s2 because those are deep in the core of the atom. All right, they're not part of the valence electrons. So 1s2 doesn't interact in the bonding of boron trifluoride. So what Pauling said is you take then this 2s2, 2p1, those 3 electrons in 4 orbitals, by the way, and again the 4 orbitals, 1, 2, 3, 4. You take those 3 electrons and you hybridize them, which means you essentially mix them together to a new energy state. And for boron, in boron trifluoride, what that means is you're going to have 3 orbitals, which are these hybrid orbitals, and they're all the same energy. And in boron's case, there's going to be an unused p orbital we're going to talk about. So you can think about it, like I said then, is You're taking these three orbitals and you're mixing them. This one just goes straight down and is unused in this case. And if they're all the same energy, then by Hund's rule, you want to keep the electrons in their own room without pairing them up. So the paired electrons each go into one orbital. These new hybrid orbitals he referred to as sp2, and that comes from the fact that it's 1 part s and 2 parts p. All right, the other p orbital is unused. So each of these new orbitals with one electron is referred to as an sp2 hybrid orbital. And if they are the same energy, one electron goes to each one, and through the ideas of VSEPR, which was all about electrons getting as far away as they can from each other, 120 degrees would be the right angles, because if they're all the same energy, one electron each, they want to get as far apart from each other as they can. So VSEPR says, yeah, this is going to be all at 120 degrees. Here is a picture kind of as to what's happening. So in this picture, it's kind of hard to see, but the boron atom would be right in the middle, all right? And around the boron, you can see are three of these kind of mushroom-looking things. It's the best way I can describe from it. Each one of those mushrooms, like here's a mushroom right here, and there's 2 and 3 of them. Each one of those mushrooms is an sp2 orbital, and there's math ways that you can draw out those structures, which we're not going to talk about right now. In reality, the mushrooms are a lot bigger, so this is what shows it right there. But because they're all the same energy, they all have one electron, and electrons want to be as far apart from each other as they can. That's where the trigonal planar geometry comes from, all right? They want to be far apart. They're 120. So when you make a molecule like BF3, it naturally takes up trigonal planar 120 degrees. So again, in this hybridization valence bond theory model, the atomic orbitals are mixed or hybridized into same energy orbitals, which they refer to as degenerate. All right, degenerate here means the same energy. And those orbitals with the same energy, the electrons are spread out, and they want to be as far apart from each other as they can, i.e. valence shell electron pair repulsion theory, VSEPR. That's where the trigonal planar comes from. At this point, in boron, you have 3 individually filled hybrid orbitals, so 1 electron per sp2 orbital. And that's what's used to make then the planar BF sigma bonds. It's kind of an interesting idea. This picture right here is pretty cool because it shows, and we saw it earlier, it shows the atomic orbitals on the top and the new hybrid molecular orbitals, if you will, on the bottom. There is the unused orbital. We won't talk about that. Now, one more thing. When you make a BF bond in BF3, the fluorine is not hybridized. All right, this picture right here of that yellow kind of figure 8 shows that singly occupied 2p orbital we talked about earlier. Fluorine is literally just hanging out with its atomic orbitals. And to make the sigma bond, which is the interaction, you need the blue, one of the blue sp2 orbitals with a single electron, and you need the yellow 2p orbital from the fluorine. They smash together and it makes the sigma bond, which is what we draw when we draw the molecule like right there. So it's really interesting idea. The central atom in the molecule is hybridized. So we would refer to boron as sp2 hybridized. But the outside atoms, like fluorine in this case, they're just using their atomic orbitals. They are not hybridized. So it's the atomic orbitals on the outside with the hybrid orbitals on the inside. They smash together to make that sigma bond. BF3 is born. The right-hand video, which I'll show you in a second, is for BH3, which is similar to BF3, only with hydrogen you would have 1s orbitals instead of 2p. So you can see there that the hydrogens 1s and stuff, they want to get as far apart from each other as they can. They're all the same energy and stuff. The trigonal planar comes out naturally. Don't worry about that SN3. That refers to something else we haven't talked about. Pretty cool. So to summarize here what's going on, in valence bond theory, all right, you look at the central atom, and we're going to apply a term to it. For boron, it's sp2 because the hybrid orbitals on that central atom came from one s and two p's. It's a little weird, but that's what that means. So we would say the boron is sp2 hybridized. We can look at other types of molecules to see other kinds of hybridization. CH4 is methane. It's the simplest in a family of organic compounds called alkanes, and we'll talk more about that in the next chapter. But for right now, what's really strange for us is that CH4 is tetrahedral, all right? Four clouds around it, they want to be far apart. And again, the same question, how do you account for those atomic orbitals at 90 degrees at best and maybe no degrees if you're an s orbital? How do you go from there to tetrahedral 109 degrees? In this particular example, we're going to use 4 atomic orbitals. We're going to use s and all 3 p's, and that's going to make 4 hybrid orbitals. Now in the BF3, we used s and 2 p's, and there was an extra p left over we didn't use. All right, but in this one, we're going to use all 4 of them, and if you have 4 orbitals with the same energy, they will naturally point in the correct positions in tetrahedral because they want to be as far apart from each other as they can. And again, it all comes down to electrons and electrons repelling each other. That's what makes them in the 109 degree angle. They want to be as far apart from each other as possible.
The valence orbitals of carbon are the 2s orbital and the 3 2p orbitals. When these atoms form methane, their orbitals are thought to hybridize to form 4 equivalent orbitals. Because each hybrid orbital for the carbon atom is composed of 1 part s orbital and 3 parts p orbital, they are called sp3 orbitals. The energies of the hybrid orbitals are the average of the original atomic orbitals.
Okay, lots of information in that, so let's think about this. Let's go to the punchline, though. If you have a molecule like carbon in methane right there, and it's in a tetrahedral environment, you will refer to that as sp3 hybrid orbitals, all right? So we would say that the carbon is sp3 hybridized. And the sp3 term, again, comes from the fact that to make this happen, we're taking 1 s orbital and 3 p orbitals, i.e. the 2s and the 3 2p's. And in the video, I like it because initially it showed the 2p's higher energy and 2s under, and that's why we fill in 2s before 2p and 2p before 3s. It's the n plus L rule once again. But anyway, if you mix those 4 orbitals together, you haven't created or destroyed any energy, and that's the first law of thermodynamics, and that's really important for chemistry and physics and all this kind of stuff. So we're not creating or destroying any energy. We're mixing these orbitals together so the s goes up and the p's come down, and you end up with 4 degenerate, which means same energy, 4 orbitals with the same energy. And the paired 2s electrons, by Hund's rule, will jump ship. You then end up with 4 individually occupied orbitals, which we call the sp3 orbitals. And again, that's because they're from 1 part s and 3 parts 3. And anytime you have a tetrahedral electron pair geometry, that's going to be due to an sp3 hybridized orbital, which is a pretty cool thing. So that's a cool video to watch. That's one of the more important videos, I'd say, of this whole class. And if you want to rewatch it, that is fantastic. But let's look now at what happens when you take the 4 sp3 orbitals and you add hydrogen.
A methane molecule forms when 4 hydrogen atoms form sigma bonds to the sp3 hybrid orbitals of the carbon atom.
Just like on the boron example we looked at earlier, that was sp2, each of the sp3 orbitals really looks kind of like a mushroom. And this picture does a better job than the video I just showed. The video makes it look like a teardrop. And if you use your imagination a little bit, yeah, okay, it kind of looks teardroppy, all right. But anyway, bear with that kind of analogy. Carbon has the 4 sp3 hybrid orbitals. And like the fluorine in BF3, the hydrogen here are not hybridized. They're just using their good old atomic orbitals. So hydrogen has a 1s1 orbital. It smashes into one of the sp3 orbitals. You've got that great overlap, which makes the sigma bond, and voila, that's how we get tetrahedral CH4. So when we talk to each other about hybridization, we talk about the hybridization of the central atom. The carbon is sp3 hybridized, just like the boron in BF3 was sp2 hybridized. Notice that the electron pair geometry is the key to finding out the hybridization. Every time you see tetrahedral, it's sp3. Every time you see trigonal planar, sp2, etc., etc. This is an overview of what we just looked at here for methane. The left-hand yellow box is a before, all right, kind of thing where it shows the 2s2, 2p2. And the right-hand side is what happens after hybridization. So you go from the s and the 3 2p's into these 4 equivalent energy sp3 hybrid orbitals. They're all the same energy, so the electrons will evenly distribute. You don't pair up until there's no more room. And then when you make the molecule, down here in the lower right kind of, the blue little blobs, those are the hydrogen 1s orbitals, and they're smacking into the sp3 orbitals. The overlap between them is the actual sigma bond that we draw, what we draw right there. Pretty cool. So that's a great way to think about hybridization or valence bond theory. The electron pair geometry is the key to determining the hybridization part. So if you have 4 bonds around the central atom, it's going to be sp3. If you have 3 bonds around it, it's going to be trigonal planar, and it's sp2. We haven't looked at yet, but you can probably imagine if you have something that's linear, it's going to be sp hybridized. The trigonal bipyramid is sp3d. Sometimes I refer to that as d sp3. I put the D first. That's an older way of doing things. It is the same thing. I like the D orbitals a lot, so it's hard for me to get rid of that one. But the new way is sp3d, fine. And octahedral sp3d2, and you got it. It could be d2 sp3 as well. So the first thing I want to point out here is that, yeah, electron pair geometry is the key to finding out what the hybridization is. And it's one of these 5 terms, sp, sp2, sp3, sp3d, sp3d2, that you're going to use to describe it. Now, we're going to come back here in a little bit and talk about what the heck the other orbitals are up for. We saw that in trigonal planar sp2 BF3, there was one unused p orbital, and there is a use for those I'm going to show you here in a little bit. We'll talk about that. The Vesper guide in your companion will just give you more information on these different terms too. Here's a question. What hybrid orbital set is used by the nitrogen atom in ammonia NH3? Okay, so this is the kind of question that you might see. And what you should do on a problem like that is first draw the Lewis structure, all right? And from the Lewis structure, you can find the electron pair geometry. And from the electron pair geometry, you can find the type of hybridization to use. Now, we looked at ammonia extensively in the last chapter. Ammonia, I'll try and draw it up here when you figure it out. Nitrogen is connected to 3 hydrogens, and there's a lone pair on it. So that's a very quick and dirty Lewis structure for ammonia. Around nitrogen, you have 3 bonds to atoms and 1 lone pair. That's like 4 clouds on the geometry and polarity guide. 4 clouds with 1 lone pair means that the geometry, the electron pair geometry, is tetrahedral, and the molecular geometry, trigonal pyramid. We don't really need the trigonal pyramid here. We just need the tetrahedral part. And anytime you have something tetrahedral, like we talked about, like NH3, it's going to be sp3 hybridized. So we would say the nitrogen is sp3 hybridized in this case. Here's some more examples of how the different things come out, especially with sp at the top, sp2 and sp3. If you have something that's sp hybridized, like beryllium dichloride or beryllium chloride, depending on how you're describing them, the bonding, beryllium itself would be sp hybridized, so that means it's only using one s and one p orbital. The two orbitals each have one electron. They're going to be as far apart from each other as they can, so it takes up linear BeCl2. And then under that you have the BF3 and CH4 examples we talked about earlier. The punchline of hybridization, though, is the electron pair geometry will help you find the hybridization. So anytime you have a linear electron pair geometry, it will be sp. And anytime you have a tetrahedral electron pair geometry, it will be described as sp3. So here's just an example of what we can do, and I want you to kind of do this, and you can pause the video if you want before I talk about the answer. But what I'm going to do is the arrows are pointing at an atom, and I want you to go through with me, and we'll figure out the hybridization of those different atoms. And again, the answers here will be sp, sp2, sp3, sp3d, or sp3d2. So the first one there, that nitrogen, the nitrogen has 1, 2, 3 bonds to other atoms, hydrogen and a carbon, and a lone pair. So 4 clouds means that the electron pair geometry is tetrahedral, and anytime you have tetrahedral, sp3 hybridized. Cool. Now let's go to the red one. That red one points at a carbon. The carbon has 4 bonds to atoms around it. 4 bonds, once again, tetrahedral, and again, anything tetrahedral, sp3. The carbon in the green box there is pointing at a carbon atom. That carbon there is connected to 3 atoms: a carbon on the left, a double bond oxygen above, and an oxygen single bond to the right. Now, remembering that double and triple bonds count as one cloud. The double bond is one cloud, the bond to the single oxygen is one cloud, and the bond to the carbon is one cloud. That's 3 clouds. So 3 clouds means trigonal planar, and anytime trigonal planar, sp2. Finally, the last one, the yellow box, points to the oxygen. The oxygen has 2 lone pairs and 2 bonds, 4 clouds total. It's our good friend tetrahedral once again. There's a lot of tetrahedral answers here. Anyway, tetrahedral once again, sp3. So hopefully you can see that this is pretty chill. If you had a linear atom, then it would be sp. If you had a trigonal bipyramid, it would be sp3d, octahedral sp3d2, etc., etc. You're probably wondering, well, maybe you are, and if you aren't, just say you are. You might be wondering anyway, why double bonds and triple bonds count as one cloud, all right? And to understand that, we need to look a little bit more detail as to what a pi bond is all about. So this compound here, the common name is ethylene. Ethylene's formal name is ethene, which we'll talk about in the next section. But the important part for us here is that ethene, or ethylene, has a carbon-carbon double bond. So if you wanted to talk about the geometry around this carbon right there, that carbon is connected to 2 hydrogens, so that's 2 clouds. The double bond counts as a 3rd cloud. It's going to be trigonal planar. So when you actually do this structure, the structure is actually flat. If we turn it on the side right there, you can see it's very 2-dimensional, like a piece of paper. This is at 90 degrees, so you can see better what's going on. So something in that double bond is somehow contributing to the overall trigonal planar structure. And let's talk a little bit more about what's happening with these multiple bonds.
The sigma bonds in ethylene come from the overlap of sp2 hybrid orbitals, one from each carbon atom.
Remember that when you draw a Lewis structure, the first line you draw is always a sigma bond. So the little animation there in the lower right shows the sigma network in C2H4. So you can see that there's hydrogens, the little circles, that's the 1s orbital, and then the atom it's connected to is an sp2 carbon. And like we saw with boron, sp2 means trigonal planar. So you'd have 3 little sp2 hybrid orbitals. There's smacking together. They're making the little overlap, which is the actual sigma bond. So you can see sigma right there, sigma right there. Here's the sigma between the two sp2 orbitals on carbon, which is cool. Here's a sp, here's a sigma, here's a sigma. Those are the sigma bonds of C2H4, all right? But what we're going to do on the next slide is we're going to look a little bit more detail as to what's happening with the other bond. Because remember, when you draw a double bond, the first line you draw is sigma, and the second line you draw is called a pi. So let's look a little bit more about what's happening with the pi bond. In BF3, there was an unused 2p orbital. And for carbon, if it's in a trigonal planar environment, you're still going to have that unused 2p orbital. And this 2p orbital can connect to the other 2p orbital on the neighboring atom. This is a real interesting phenomenon. And remembering here that the 2p orbitals are always at 90 degrees, what happens when you make a pi bond is those unused p orbitals are like above and below the plane of the molecule. So let's back up a little bit. This is showing the 2s2, 2p2 atomic orbitals as they're being hybridized, in this case to 3 sp2 hybrid orbitals. And this part is why it's trigonal planar, because they're all the same energy and stuff like that. However, there's also this one extra electron in an unused 2p orbital. And that one electron in that unused 2p orbital is going to be used for the pi bond. And it does something really interesting. Now, it's kind of hard to see here, but this yellow blob is basically the trigonal planar. I've drawn it kind of coming out at the board, but you want to think of it as being flat. So it's like a flat triangle. And the unused p orbital sticks up a little bit above and a little bit below the triangle, all right? So, oh man, again, my drawing skills are just horrible here. But let's say you have like a triangle, and then it's kind of like a trigonal bipyramid, I guess. There would be an unused p orbital sticking out above and below the trigonal planar geometry carbon in the middle. And this extra 2p has an electron inside it. So if you have two of these 2p orbitals next to each other, they communicate with each other a little bit.
The pi bonds arise from the overlap of unhybridized p orbitals, one on each carbon. Note that pi bonding electrons are found in a region above and below the sigma bonding region.
So again, you've got these carbons, and they've got these unused 2p orbitals, which are above and below. So in the middle right here, this would be all of the sigma bonds, all right? And there's sigma bonds right there, all right? But the pi bond arises because the 2p orbitals are interacting with each other. And you can see in that video, it looked a little bit like bread. That's the closest thing I can use for an analogy here. And there's a piece of bread like on the top of the molecule, and there's a piece of bread on the bottom of the molecule. So a pi bond is those extra 2p orbitals like talking to each other. It literally is like it. And it makes an electron kind of spread above and below the molecule. In the C2H4 molecule, I like this description because the sigma network is kind of like the quote-unquote meat of a sandwich. All right, now, I'm a vegetarian, so I'm going to use vegetarian meats, but you use whatever meat you want to, okay? No problems here. But anyway, the sigma network is like the quote-unquote meat of the sandwich. And the pi network is the bread, and it's both above and below. You get 2 slices of bread per pi bond. Woohoo! Anyway, that's what makes this sandwich of C2H4. It's really cool. Now, this bread is what makes the molecule flat. All right, we saw pictures earlier. It was a totally flat molecule. That's because there's this pi bond both above and below the molecule, which is really cool. So backing it up here, I get really excited by this, you can tell. These extra 2p orbitals, in carbon's case anyway, are going to talk to each other on the adjacent carbons. And when they quote unquote talk to each other, it makes a pi bond. But pi bond has two components. One part is above the molecule and one part is below the molecule. All right. So a pi bond actually has two parts to it. And that's what we saw in that little video just now.
When we look at both sigma and pi bonds, we see that the CH2 fragments are coplanar and that ethylene is a flat molecule.
So this video shows the sandwich, quote unquote, the bread above and below that molecule. That's the pi bond. That's the second line we draw. And the quote unquote meat of the sandwich is all this stuff in the middle. That's the sigma network, all right? So it's really interesting. When you draw C2H4 as a Lewis structure, all right, initially you have just a bunch of single bonds. That's the sigma network. As you draw the second bond to make the pi bond of the double bond, that's adding a piece above and below the plane. And this pictures up here are trying to show it. So this part right here, that's the bread network, that's the pi bond. And again, the pi bond is both the light blue and the purple parts together. Pi bonds have two parts to them. And then all of this part right here, that's the sigma network, the meat of the sandwich, all right? And it's really neat how they all come together. So this is the combined picture of our sandwich, all right? And again, the blue and the purple is the pi bond. These little dudes are the hydrogens right here. Most of this yellow here is the sigma network. It's really cool how this comes together. Sigma bonds in valence bond are the first thing to form, and it's like the base part, the meat of the sandwich. And if you make a pi bond, then it's like bread above and below the structure of the molecule. This pi bond makes these molecules flat in this region. Pretty exciting. Acetylene is C2H2 in acetylene torches. The official name for acetylene, we're going to see in the next chapter, is ethine, but we'll talk about that later. Ethine is HCCH, and when you draw a Lewis structure, this has a triple bond. So get ready, all right? The first part right here, the first yellow box, shows the sigma network in acetylene, all right? It shows just the hydrogen carbon sigma bond, which is right here. Here's the carbon-carbon sigma bond between the two carbons, and here is the other carbon-hydrogen sigma bond. So this part right here would be like the HCCH part right there. It's just showing the sigma bonds. But the Lewis structure, which is over on the left-hand side right here, the Lewis structure has not just one pi bond, but two pi bonds. Remember, a double bond is 1 sigma plus 1 pi. A triple bond is 1 sigma plus 2 pi bonds. And in this case, it's going to make two of these slices of bread. So the picture, the yellow box on the right, this is the first pi bond. You can think about it as bread above and below the acetylene molecule. But get ready, this is kind of cool. This is the second pi bond. It also has two components, but instead of being above and below, it's like left and right of the molecule. So you try and draw this like it is right here. It totally fails because there's too many bonds like all coming together, man. It's a crazy sandwich. But again, you can think about this as like some kind of super sandwich where instead of having just the bread above and below, now you have the bread to the left and the right as well. Mega sandwich. But anyway, sorry, that's I must be hungry. Anyway, Prophet back on. C2H2 is different than the last one because there are two pi bonds. And so one pi bond will be above and below, two components per pi bond. The other pi bond will be left and right of the molecule. And again, in the middle is where all the sigma network happens. It's pretty cool how this stuff comes together. So this is why now in a Lewis structure, you think about double bonds and triple bonds as just one big cloud, because these pi bonds just kind of add on to the already existing sigma network. It's one big cloud of electrons, whether it's double, single, or even a triple bond. It's just bigger and bigger clouds, basically, that you have to deal with. How many total sigma and pi bonds are in acetylene, C2H2, all right? Well, I covered up the picture there, so let me draw. What you would do, first of all, if this was your problem, is you'd want to draw the Lewis structure for acetylene, aka ethine, and stuff again. And when you do that, it looks like this. It has a triple bond between the two carbons, and there's single bonds between. Now, the triple bond, like we said, is 2 pi's and 1 sigma. So each of the lines is a bond. That would be 2 pi and 1 sigma right there, all right? And so it's tempting when you're doing these kind of problems to answer, for example, B, because that's it. But the whole molecule also has a sigma bond right there. And over here is another CH sigma bond. So if you count it up, there's actually 1, 2, 3 sigmas and 2 pi bonds. The answer is D. So I put this up there because if you'd happen to see a problem like this in the future, don't forget to count the CH sigma bonds, or maybe there's a CH3 or something like that. Look at the whole molecule, not just the double or triple bond. Another interesting factor when it comes to double and triple bonds, a single bond can be rotated very readily. So this picture right here shows a carbon-carbon single bond, and carbon-carbon single bonds will rotate readily. But if you have a carbon-carbon double bond, it's very difficult to have the double bond twist. So if you wanted to put, say, this hydrogen right there and this hydrogen right here, probably would be very difficult to make it happen. And that's going to be important for us here in a little bit. We're going to consider in Chem 222 that single bonds have free rotation, which means they rotate like propellers very easily. But we're going to also assume that double bonds, and triple bonds for that matter too, don't rotate. You have to break that pi bond. You have to rip the bread in half, essentially, rotate it, and then reform the bread, and that's a pretty high energy process.
The carbon-carbon double bond prevents the ends of the 2-butene molecule from rotating freely relative to each other. As one end rotates, the energy of the molecule increases greatly because the carbon-carbon pi bond must be effectively broken. That is, there is a large energy barrier to rotation around the carbon-carbon double bond. Butane can rotate easily about its carbon-carbon single bond because the atoms of its methyl groups repel each other rather weakly. Rotation about this bond is accompanied by a small energy barrier and occurs readily at room temperature. The two sides of the molecule are therefore constantly spinning with respect to each other.
Lots of things in this video we need to talk about. First of all, the upper left-hand version has a double bond. That molecule has a carbon-carbon double bond. And in the lower right corner, that compound has just carbon-carbon single bonds. And if you look at the difference in energies, all right, like for example, on the upper left one, 233 to 26, well, that's about 230 and 30. So it's about 200 kilojoules per mole difference, roughly, between those two values. In the lower right-hand corner, it's 78.49 is about 80, and the other one's about 20. So 80 minus 20, it's about 60 kilojoules per mole difference. And there's a big difference between 200 kilojoules and 60 kilojoules. And that is what allows the single bonds to rotate pretty readily. So we assume that compounds like butane or N-butane will rotate readily, all right? There's differences here in the energies, and that's something you'll talk about in organic chemistry, which is the second year of chemistry. At this level, we don't need to worry about like why there's a small gap and then a big gap and then a small, and that's for your organic chemistry class. But anyway, it's relatively easy to rotate a single bond. On the other hand, the double bond, which is up here, you have a much larger energy gap to make that happen. There's two ways to name these kind of compounds, especially the upper left one. The old way was trans-2-butene, but the current trend is to call it trans-but-2-ene, and this is something we'll talk about in the next chapter. Likewise, in the bottom, butane technically would be N-butane, and we'll talk about about all this later. But regardless, the important part is that if you're trying to rotate a double bond, it's probably not going to happen. It's much higher in energy to make that transformation occur. On the other hand, single bonds will rotate very easily. And this will have implications for stuff we'll talk about here pretty soon.